Okay, everybody, thank you for joining us today. Today we're joined by Thomas Burbine, if I said that right, from Mount Holyoke College, who is applying to join us as a senior scientist. So, Tom, go ahead and take it away.
Okay, thank you very much for letting me speak. So I'm going to talk about how well can we determine the parent bodies of meteorites. I find this fascinating. So this is the thing I kind of been working on the past few years. And the two pictures there, I was in Japan years ago. I got a picture with sumo wrestler, and then the one on the right, I got a picture with John Cena. It was very nice. I always put those up for good luck. And I want to get down to some just a basic information. There's about 1.5 million known asteroids. And pretty much they range from Ceres, which is now dwarf planets, about 1,000 kilometers in the diameter, Pallas and Vesta, about 500 kilometers in diameter. And they go down to tens of meters if they're in the nearest population. So a huge range in size. There's about 80,000 known meteorites, and that includes meteorites that are paired with each other. So huge difference in numbers. But if you look at, and this is work I work with Richard Greenwood, who's a picture at the top right. There's about evidence in our collections about 100, 150 parent bodies. That's what we think we have evidence for in our collections. And to find a parent body, and I'll talk about that a little later, you look for similarities in mineralogy, and you also look similarities in isotopes using different things. And this number, if you, is very close to the number of known asteroid families. And this is work done by David Zaforny. And the latest number is about 360. So, and on the right is a plot of all the asteroids a few years ago. And the red are the near Earth, the green are all the main belt, and then the blues out there are the Jupiter Trojans. So you can see there's a lot of asteroids out there. And this is a plot I made a few years ago of like some of the big asteroid families. An asteroid family is it's a where the proper elements, the distant from the sun, semi-major axis, the inclination, the eccentricity kind of clump together, and they're named after the largest object in the family, and they're scattered throughout the belt. And most people think if you have a relatively recent disruption, it creates so much material coming off that kind of like goes to these meteorites supplying resonance, like the 3 to 1, 5 to 2, and then becomes near Earth crossing orbits and then reaches Earth. Because so much material is being thrown off, some of it can get to the Earth and land on Earth, and then we have the meteorites. So these families are typically thought to be where a lot of the meteorites we get today originate from. And as I said before, a huge disparity, about 1.5 million known asteroids, only about maybe 150 postulate parent bodies. And maybe the asteroid belt only contained a few hundred, like original, what we call planetesimals. These were broken down. All the asteroids are almost all of them fragments of bigger bodies. And it's also possible we're preferentially getting only meteorites from a relatively small number of parent bodies. It's a few parent bodies that are dominating what we see on Earth today. Uh, and also, maybe you could have two parent bodies that are almost exactly alike. They are mineralogic and isotope similar. So you really can't determine them. So maybe a few bodies formed and you can't really tell the difference from just a few fragments. So there's all these questions we're trying to answer. And this just shows how we classify meteorites. There's the chondrites, they haven't been heated, maybe a little heating. Chondrites melted and part of differentiation. Then there's also what's called the stony iron meteorites, the pallasites, which are thought to be the alvine mantle, the boundary between the mantle and the core. There's also metasiterites, which is thought to be an impact on the basaltic body. Then there's iron meteorites that are thought to come from the core. There's also primitive achondrites, which melted some, but didn't seem to have full-scale melting. As I said before, about 80,000 known meteorites, about 40, approximately 40 meteorite groups. And then there's all these ungrouped irons. Irons you can't really group with other meteorites. You need to have five to have a group. The thing with iron meteorites is they're very strong, hard to break down. They can last for billions and billions of years, much longer than, say, something that's made out of silicate rock. And this should just show some pictures. That's a CV, and you can see up there. You can see a CAI. You can see the chondrules, the H chondrite. You see the metal, LL chondrite, and then the ones below it are the differentiated. Albright is pretty much iron-free ensitite, and this is the product of something that melted and differentiated. So the lighter stuff goes to the top, the heavier stuff goes to the core. You also have iron meteorites. You see this women sand pattern of camosite and tanite. Then you have a palisite, very pretty meteorites, olivine and metal. And a parent body, people defined it differently, is the original planetesimal where a meteorite is derived from, the original huge body that formed. And this just shows a differentiated primary, maybe like Vesta, where it's the parent body that some collision, there's an impact on it, pieces come off, and either they go directly to Earth, they go to a resonance and go to Earth, or they become like an NEO, and then maybe you get the fragment of an NEO. And this would also work for if this was undifferentiated, just a big chondritic body. But just kind of show that you have to hit the body, disrupt it somehow to get pieces off. These pieces drift, get to a resonance, and either you find them there directly or an NEO, and a piece comes off the NEO and thing. And this is an oxygen isotope diagram. This is a plot of delta of oxygen 17 divided by 16, and on the y-axis. On the x-axis is the kind of oxygen 18 divided by oxygen, also by oxygen 16. And this is used because meteorites that we think come from the same body tend to fall in these things called fractionation line. All rocks from the Earth fall in this terrestrial fractionation line here. Some of these meteorites fall above, some of them fall below. All the meteorites we think come from Mars fall in their own like little region of the space. And we think that if you're from the same parent body, you should fall on one of these fractionation lines. So the people, I love this. This is one of my favorite diagrams, kind of originated from Bob Clayton. This is one way to look at parent bodies. You need to have similar oxygen isotopic values. How similar is a question, but similar. But that's one way to try to identify different parent bodies. And spectrally, asteroids reflect light differently depending on their surface composition. This is called the Buss-De Mayo taxonomy. Bobby Buss, who's a PSI member, and Francesca De Mayo. Different asteroids reflect light differently in the visible and the near infrared. And if you look at these enough, the S complex has absorption features due to olivine and pyroxene. C complex seems to have reflectances similar to carbonaceous chondrites. Then there's the X, relatively flat. Maybe they're organic rich. Some of them may be thought to be metallic iron because this does not use albedo, so you don't know how bright or dark it is. So it's a thing. Then you have these things called M members, like Ds are thought to be organic rich. And then some of these have absorption features. Qs have compositions similar to ordinary chondrites. I'm going to talk a lot about Vs. Vs have very characteristic absorption bands due to low calcium pyroxene, and the V is for the asteroid Vesta. These are very characteristic. Seem to be very abundant in the asteroid belt, and they're very easily to distinguish. And you also have the A types. This feature is due to olivine. We measure in the lab and then we compare them to the asteroid. But this is how we classify asteroids, by how they reflect light over a number of wavelengths. And how do you get this reflectance spectrum? You have the sun as the source. The asteroid, which is Vesta, reflects light. You go to a telescope. This is the IRTF. You have a prism, a grism, a grating. It disperses the light, and you measure the intensity of the light. And to get the reflectance, you have the object you want the source is the sun. So you want to divide the flux from the asteroid by the flux by the sun. But the problem is the sun's up during the day. It's too bright. So you take a star like the sun, a standard star. And if it's similar, you can divide the object by the standard star, and that gives you how it reflects light, and then you get these specific absorption bands. The sun peaks in the visible and the near infrared, so you got a lot of intensity. The atmosphere is relatively transparent, and minerals have very specific absorption bands. There's other wavelengths, but this is one I primarily use. And most of like in these pyroxenes, it's due to iron 2 plus absorptions due to a transition due to the iron 2 plus in the pyroxenes. And then you can group different asteroids, meteorites with different types of asteroids. This is a table I made a few years ago. You can group ordinary chondrites seem to come from S types. Carbonaceous chondrites seem to come from C types. COCV seem to come from K types. And you can argue about where they come from. But the question is, how specific can you get? And that's what I've been trying to work on. And this work by Grady and Tedesco is if you can get the composition of the asteroids and try to link it with a particular composition, C tend to carbonaceous, D organic rich, S with the ordinary chondrites or some alvine pyroxene assemblage, E's with the aubrites, you can try to map the asteroid belt. And you can see there's actually trends there. Some of the asteroid classes are more towards the beginning of the belt, the interior. Some are farther out. There are trends there. And this is work by Francesca De Maio and Benoit Carey. They were able to estimate the mass, and you start seeing trends where the S types tend to be more in the interior of the belt, the C types tend to be outer, and try to get what is happening. And this is work by Kevin Walsh. His theory called the grand tack is the S type form close to the sun, the C types form far from the sun. The Jupiter and Saturn start moving in and they start scattering stuff in, and that's why we have the asteroid belt. So when I came up in school, we originally thought where they were is where they formed. Really, no one really believes anymore. Everything has been thrown in, and this is the only stuff that's a stable orbit. Didn't go in the sun, didn't go in the planet, didn't get thrown out, got a stable orbit. So this has changed over time. And there's been the three sample return missions that this has changed the way we think. Hayabusa, Hayabusa 2, OSIRIS-REx. These are not the parent bodies. These are like sort bodies. They're hundreds of meters in diameter, too small. But these are the best we've done so far, and I'm sure we'll do more in the future. This is the Hayabusa, and as you can see, there's nothing really in the container. This mission landed, but it didn't fire the pellet, but it got some material. And before the encounter, a lot of people, not everyone, thought this looks like a reddened ordinary chondrite. And the same type of absorption bands. And this is work by Tomoki Nakamura. They looked at the sample, and the composition was an LL chondrite. It had the phaolite, which is the iron part of olivine. It also had the ferrocylite, which is the iron part of the pyroxene. It matched an LL chondrite, which is what work done by Rick Binzel actually predicted. And then we had Hayabusa 2, and this is Quinchoma. This is our plot at the bottom. This got a lot more material, grams of material, right? And before the encounter, they knew it was going to be a carbonaceous chondrite from the spectra. They were trying to say it was some heated CM. They weren't sure. And then when they got the sample, these are abundance plots. You go to more volatile for lots of elements. And this is the ratio of the concentration versus the CI meteorite, which have compositions as close as possible to the sun, to the solar nebula. And you can see it's very, very flat. This has a composition similar to a CI. And this was a little surprise because it wasn't a prediction. They knew it was carbonaceous, but they didn't know exactly it was. The tantalum here is because the pellet, the bullet they fired had lots of tantalum, so you don't believe that. But everything else, if you take the ratio, it's close to a CI. Interesting. And then this is Dante. This is OSIRIS-REx. They got lots and lots of material. You see how much they got. Before the encounter, this is visible. This near infrared. This is the 3 micron feature due to water. They predicted maybe a CR, some type of CM. Also, it was CI-like. They're a little more reticent about saying it's a CI because they're trying as much as possible to compare to the meteorites. But you can see the blue line, it's very similar to a CI if you take the abundance. So another CI-like. So we've done encounters, we've got material, and we've identified compositions. But the spectra, it's still kind of a guess. It isn't, we can't tell exactly yet for at least these few, for the Bennu and Ryuga. And there's also cheap sample return. There's Peter Jennickson's. There's an asteroid collision course. exploded in the atmosphere, rained down their Sudan, and they got samples, which is amazing. And they also got a spectrum. This is the F class. This is a class not used, defined by Tholen in his thesis. It's very flat. And it was a uralite. It was very dark, but you didn't see any absorption features. If you saw this a spectrum from your telescope, you assume it's probably a carbonaceous chondrite. So you got to be a little careful just making interpretations. So it was a primitive A chondrite. The samples there, plus also they had some chondritic fragments they too that would seem part of this rubble pile. So interesting. So we've been making progress. So this is a paper I published in 2024 with Richard Greenwood, Bidong Zhang, and Paul Buchanan. How many Vesta-like bodies exist in the asteroid belt? Vesta is the asteroid number 4. It's one of the largest in the belt. And I wanted to see how many of these bodies existed once. And this is our best known parent body. If we have Vesta wrong, then pretty much we don't understand anything. About 500-kilometer diameter, second largest body in the asteroid belt, studied in detail by the Dawn spacecraft run by Chris Russell, has a distinctive spectrum. If you look at the spectrum, visible and then wavelength versus reflectance, has the same absorption bands of low calcium pyroxene, similar to the HEDs, howardites, eucrites, diogenites. You see the same bands, you see it. And there's also these small bodies called vestoids, about 5 to 10 kilometers in diameter, which are scattered throughout the belt. So it was controversial because Vesta's not that close to a resonance, but Rick Benzo was able to identify bodies with this type of spectrum between Vesta and the resonances. So it appears that it almost certainly is the parent body of the HEDs. And these are picture of the HEDs. There's a eucrite, mainly a pigeonine plagioclase. There's diogenites, mainly orthopyroxene. And then the howardites are mixtures of this material. So all three of them come from the same parent body in the mixture. Eucrites are thought to come from the top layers, diogenites lower, and the howardites are mixtures. And these are very abundant on Earth. But in the 90s, they identified a body called Magnia at 3.14 AU. Vesta is about 2.36 AU, so this was very far across a number of resonances, and this had this same type of HED-like spectrum, but it was very, very, very far from Vesta. And dynamically, you can't really get it to originate from Vesta. So this was a mystery that there may be other Vestas that formed in the asteroid belt, other Vesta-like bodies. So this spectrum, this V-type spectrum, is very easy to identify. You could just take a spectrum or just get a few colors. If you go here, you can see how distinctive it is. It's very easy to identify with just measuring reflectance of some objects. So it's very easy. And they typically have diameters less than 10 kilometers. Magnia is a little weird. It's farther. The first diameter is about 17 kilometers. It's bigger, it's thing. And then while all this was happening, they had found some HEDs with these anomalous oxygen isotope values that weren't similar to the typical HEDs. Like the most famous one is NWA 011. This is Northwest Africa. They found one. If you take the oxygen isotopic values, it didn't match the typical HEDs. And there's also a lot of iron meteorites. Vesta is a body that differentiated basaltic crust, plagioclase basaltic crust, then probably an olivine mantle in the interior, and then a core. That's what we think is the composition of Vesta. But to get this crust, the basalt, you have to differentiate. You have to pretty much melt the whole body, and then the core with the metal-rich material that would sink to the core to make the iron core, sink to the middle and stuff. So there was an indication that more Vestas formed. So I wrote this paper as how many once existed. Could I actually make an estimate? Because I thought that was going to be interesting. And Vesta-like, you have to define it. We broadly define it, Vesta-like body as a differentiated asteroid-sized object with a crust composed predominantly of low calcium pyroxene plagioclase feldspar. That's basalt. So the thing forms, it's hot enough, the heavy things sink, and the lighter stuff go to the crust. So my strategy is that there's this guy named Sir Francis Galton. People guessed the weight of an ox at a fair, and he found that the median and the mean of the guesses of the weight judging was better represented than the closest guess. So I was going to look at the astronomical evidence, the HED evidence, and the iron meteorite estimate, take the average of those three, and I'm going to assume that's the best guess of what the number is. So I thought that, I don't know, I thought that then you take evidence from a few different sources and then make a guess what the composition, what the number of HED Vesta-like bodies was. That would be the most accurate way to see. Instead of taking one number from one piece of evidence, take three, and then take the average. The astronomical evidence is hard to determine. This is a plot I made. Yellow is all the asteroids. Anything that was somebody labeled as a V type through some survey, there was lots of surveys, I gave like a dot. Green are in what's called the Vesta family. So these have similar orbital elements to Vesta. If you had near infrared spectra, I put like an open orange circle. Vesta's the red dot. And then Magnia is this larger circle out here. And so you can see all this stuff seems to be centered around Vesta. Then it's kind of goes over the resonance and you get some more material here. But it was very hard to determine how many bodies. There seemed to be kind of two, at least two. There's probably more, but I just tried to be a little cautious. I said the Vestoid evidence is pretty much evidence that there was two of these, maybe two of these bodies. And there's other stuff here, kind of travel and stuff. And these new 6 and 3 resonance are thought to be just applying stuff there. So Vesta's right here, and then there's all this stuff. Vesta's part of a huge family, and there's all the material out. But there's also a lot of these V types spurred out and not even part of this family. Then we looked at the HEDs, and this is from the oxygen isotope, and this is big delta 17, so it's a little turned on the side. Most of the HEDs, this work done by Richard Greenwood, fall on this line. They call it the eucrite fractionation line. But some of the eucrites have slightly different oxygen isotope values and start falling off. And then you try to make a guess, like how many bodies. And we kind of said there may have been like 7 of them. Not all are plotted. There's also some mesosiderites, and they're parts of HE-like material and also metal. They're thought to be maybe a metal body hit the crust of another body, and some people argue it could be Vesta. Other people argue it isn't Vesta. And there were some very isotopic anomalous HEDs, NWA 011, a few of them, and then which aren't plotted. But we looked at the oxygen isotope evidence and said that there may be maybe like 7 Vesta-like bodies, including the HEDs. It's big delta 17. So in the oxygen isotope plot, it's kind of like at an angle. This kind of like is the distance from the terrestrial fractionation line. So it kind of turns it on the side. And then Bidong was he was able to he looked at the iron meteorite evidence, and to get an iron meteorite, you get if it cools in the core, you get what's called like a Widman-Stann pattern because it had to have cooled very slowly. And you tried to look at how many of these iron meteorites could potentially come from like a Vesta-like body. And we got up to maybe 22 looking at all the iron meteorites with all the groupings. And maybe if you include Vesta, it makes 23. So the iron meteorites, the only way you can get them is to really disrupt the body. So it would take all the material, all the come out, and all be left there to be the iron meteorites. All the other stuff was broken apart and probably were broken down. So we tried to make an estimate how many of the bodies would have fully differentiated to make what we call this Vesta crust. And not all the crusts are HED-like. There's other types of differentiated meteorites called angrites, aubrites, andesites. So this number is most certainly an overestimation. So what we did is I thought the best way is to take the 3 numbers and you just average them. So if you average our 3 estimates, you get like 10. So there may have been like 10 Vestas that formed. Only one of them survives today. Only one of the tech Vesta, were observed by dawn, only 10 of them probably survived. The astronomical evidence underestimates the HEDs. Maybe it's close. And then the iron meteorites is probably an overestimate. And you only have Vesta today that's intact. Everything else is broken down. So this was just a way to see, can you do a number? Can you make a guess? It's hard to say how close we are because there's no thing, but I wanted to see there seemed to be a number of bodies differentiated like Vesta, and the only thing we could really tell is they seem to have slightly different oxygen isotope values. And then this is a paper I just submitted this, I think a week or two. Was it last week? I just submitted it a few days ago. And we wanted to see, can we do this thing with CM? They were having a special issue on CM chondrite parent bodies. So I said, okay, let me write a paper. So I'm working with Richard Greenwood, the oxygen isotope expert, and this Aman Kariu, who is a good friend of mine down at the down to Learn Planetary Science Institute. CM chondrites are the sixth most common meteorite to fall to the Earth. They're the common type of most common type of, I should use common twice, of carbonaceous chondrite. About 800 meteorites in our collection. It's primarily matrix, right? And then there's this thing called chondrite, which is iron, magnesium, silicate, and then they also have serpentines. And there's all these intergrowths of chenillite and chondrite. So if you look at them, they're very dark. There are some light areas that seem to be heated, but most of these are very dark, and you really can't see what minerals are there. And there's different types. They're usually what's called CM2. There's a way they classify carbonaceous chondrites. CM3 have been the least heated. You go 2, they more aqueously altered. CM1, very aqueously altered. 4, 5, and 6 are ways for like heating, but they're usually not they're for like the CK chondrite, but there's H3, H4, L, and things more heated, but the classification we really care about is the CM2. And there's all the way that it's kind of reversed on the scale. There's all these different minerals depending on how much heating there is. So the CM2s have been aqueously altered. They have phyllosilicates in them. They're very dark. There's lots of organics and things like that. And we looked at the oxygen isotope evidence in these CM2s, and you could see they tend to fall in a nice line. There seem to be two kind of groups in the oxygen isotope diagram. There may be more, but there seem to be like two groups where some of the lower, these have been more aqueously altered, the 2.1s, 2.2, there's a finer scale, and then some of the ones that have been kind of just minimally aqueously altered seem to be a break. We're not sure what the meaning of it is, but the total meaning. And this one of us called this Winchum, which actually fell during COVID, and you can see a black spot there, a very fresh meteorite. There's also other types of CMs. There's a hodgepodge of CMs. There's CM anonymous. There's CM1s. You wouldn't expect to get the zero-point micron band because that is only due to having this concentrate. There's a transition. There's a transition between the iron 2 plus and the iron 3 plus. So you only see the feature in this when you have this particular mineral. When you don't have this transition, you don't see it. It's a transition between the iron 2 plus and the iron 3 plus. So you wouldn't expect a 0.7 micron band because they're slightly different in mineralogy. And there's all these different types. It's very kind of complicated. But here's a picture of the band. So you see this band right here, and you can see this is Fortuna, which is it's a CH type asteroid, and you can see this absorption band. Red is Lu 90500, the CM2. You see this absorption band here. It's almost a perfect match spectrally, maybe a little off in the UV, and this is due to this charge transfer absorption between the iron 2 plus and the iron 3 plus. And other types of CM chondrites, which are maybe aqueously altered, the lower the number, the more aqueous the alteration is. You can see the mill, you don't see the feature. This feature is probably due to magnetite. You don't see it in this ungrouped C2 ungroup, you don't see it. So this is a very characteristic absorption feature of these CM2s. It's very weak. It's like 5-ish%, but you can see it in the reflectance spectra of these CM chondrites. And this is just as so in the Bust-to-Male classification. These are CHs, CGHs. You see this feature right here at about zero point 0.7 microns. You also see in CGAs, they tend to have a little stronger absorption feature. You don't see it. So these things are called CH chondrites. The taxonomic class for the asteroid CH or CGH. This is a plot of the CM2s where they've tried to look at it from the families. Which asteroid family should be supplying a lot of these meteorites? They look for asteroids in the belt which have these absorption features similar to a CM, and they would try to group which asteroid family should be supplying a lot. And you can see up here, you see Adionium up here at the top. This is work. This is work where they found where these are slightly that these families that they've been able to link to have these that have this spectral feature, this 0.7 spectral feature, they've been able to say seem to have CM chondrite compositions should be supplying, and they believe that at the top these are the larger asteroids, the kilometer should be supplying lots of kilometer-sized fragments, while at the bottom the CMs these ones should be supplying a lot of the smaller asteroids, about 1 meter in diameter. So they've looked at the same one. So they're saying Veritas should be supplying a lot of the small fragments, and then Adiona should be supplying a lot of the larger fragments that have this zero point 0.7 micron feature, which is found in these CM chondrites, CM2 chondrites. What I did was I just plotted them all these objects that were either labeled as a CH or a CGH that have this zero point 0.7 micron feature, and I just plotted them all, and I plotted the ones in families. And what I found is that it's all over the place, that there's big ones. The biggest circles are about 216 kilometers in diameter, and you find these objects all over the asteroid belt. There are some in families. A lot of the families seem to have members, but it's not as characteristic as like with the V types, where you have one object and everything's to be coming from it. There seems to be lots of these objects in the asteroid belt. They seem to be common. And I don't think you can maybe say that it's more likely to come from some family thing, where the Veritas family's here, which is thought to have the smaller fragments, and then and then the other families, I think it's this family. Then no, it's the family. Aragoni families like here. So you could see that there's lots of families that could be supplying these CM chondrite asteroids, CM2 chondrite asteroids to Earth. And some of them aren't in families, maybe they're older. But the problem is there's no direct I don't think you could really say where the CM2 chondrite parent body is. There's too many objects in the belt with no specific trends to be able to say that something is coming from something else. So my conclusion from looking at that is this CM2 material that has this zero point 0.7 micron feature is spread throughout the belt. And it's extremely determined at a specific parent bodies. You might be able to say some probability coming from some other, because maybe it's a young family, but you really can't say that it comes from some specific parent body. The CI material is probably much more abundant, the stuff that has the composition close to the sun, but because there's no specific absorption feature, you can't say. You need a specific absorption feature to try to make any of these correlations. And the last thing I'm trying to work on, and hopefully I can submit a proposal through PSI, is we're trying to generate an asteroid taxonomy that actually classifies bodies mineralogically. This Bust-to-Male, which works very well, classifies things by how they reflect light. Can we actually classify objects more mineralogically? So we're using machine learning, which Darby Dyer is one of the proponents of. You can can you use it? Can it learn from the data and then try apply it to unseen data? We're training on meteorite spectra, and then our plan is to classify asteroids. It seems to work. We're still working on it. The problem is many of the asteroid surfaces are space weathered, so we're going to probably have to artificially space weather some meteorite spectra to ultimately classify the asteroid spectra. The meteorites tend to be fresher, not have space weather surfaces. So we're trying to figure out how we may have to artificially space weather them. And we want to determine meteorite analogs for asteroids and then map the asteroid belt. That's our ultimate goal. So our plan is to train on meteorite spectra from Relab, which is the biggest source of spectra, then classify the asteroid spectra and then give them meteorite classifications. However, this is a plot I made, the distribution of spectra. This is some of the classes, because we went to Dawn, went to Vesta, we have lots of HEDs. We have lots of CMs. They're very common to fall. Some of the classes are very new, and you need spectra to be able to train it using the machine learning. You need a lot of spectra. You can't, you either, we tried before to generate like artificial spectra, but the best is to have real spectra of real meteorites. So my hopefully submit a proposal is we're trying to make more and more, get more spectra of rarer meteorite types, get more spectra to get these numbers here. So maybe get 50 of each class. And then when we, use the machine learning, we could train on a data set with a large number of samples. That's the thing, because there's a huge disparities in the number of samples, depending on some are common, some are just more popular to study, and some are much rarer. So we're trying to increase the number of spectra of all the meteorite classes. So that's the proposal I'm hoping I'm writing, or hopefully writing and stuff. But we want to get spectra of rare classes to have more numbers. So when we do the training, the machine learning, we have a set of data we can train on that there aren't huge disparities in numbers. And I think so. We made progress, but the main problem is it is very hard to conclusively determine parent bodies of meteorites. We need main belt sample return, which hasn't happened yet. You can say that a probability, but you can't really say it has to come from some asteroid. Maybe Vesta, but everything else is very difficult because there are just too many other objects. Things aren't unique, and that's the problem. So, any questions?
Thanks very much, Tom.
Yeah.
Let's see. There's a conversation happening in the chat that I think that it would be helpful to talk about
Okay.
about aqueous alteration and how that happens. Um, I have another question about space weathering too, but let's go to the aqueous alteration first. Mike Hecht, do you want to just talk about your question? Tom may have some
Unmute. Okay,
perspectives
here I am.
on the
I
question
had to
for
unmute.
asteroids, and then we can get to Mars too.
Yeah. Yeah, and this is just, I put something in the chat because I've wondered about this for a long time, and your talk kind of triggered it. I was trying to understand how aqueous alteration happens in the first place on a body that isn't have enough, gravity to support atmospheric pressure above the triple point of water. And my assumption is it must happen underground where water is totally sealed off, and the head pressure, the water vapor pressure, pushes it past the triple point. But I wanted to understand if indeed that's the thinking, or if I'm missing something about the surface properties.
Yeah, it would have to occur underground. It couldn't really be exposed to the atmosphere. There is water out there that must have been incorporated when these things are coming together. And then there's a heat source, probably aluminum 26. So that causes, my basic knowledge is it causes a reaction between the rock and the water, and it's able to hydrate the silicates.
Okay, but then water, the problem I had was that there's very limited conditions under which water can be in a liquid form. Maybe it doesn't need to be in a liquid form for that process to happen. That's another possibility. I just don't know.
Yeah, because the body size is the maximum size is probably like 1,000 kilometers in diameter, probably at the most, hundreds to kilometer size. I'm trying to answer your question. The problem is you do find hydrated silicates in there. Yeah.
And
So
I'm just trying to understand why. And part of the reason I was trying to understand why is because we have the same kind of struggle with, even with case of Mars, where we have a hard time explaining surface conditions that would have been wet and had a lot of surface alteration on the surface. And I keep thinking, well, well, what about asteroids, which are even more difficult? So that's why I'm asking.
Yeah,
And
yeah, no,
this may be
that's
a
a good
rabbit
question.
hole that we don't want
Yeah,
to go
yeah.
down.
I think the main thing is this had to have occurred deep in the bodies. You had to have occurred. I don't think it would have occurred anywhere near the surface, but it would have had to occur relatively deep, where you have water and you have rock. That'd be my thought. That it's something that's occurring way into the interior of these bodies. And then what happens is it's occurring in the interior. Most of these bodies are fragments of very few bodies are the original size. They must have been assembled after that occurred and then reassembled. So I think you can get it if it occurs deep. That'd be my guess. But I don't know if are the pressures high enough? That's my
Yeah,
question.
well, deep as long as it's sealed, but then
Yeah.
then what this implies is the body has to break up so that you can find those fragments in the meteorites.
Yeah,
Again, I
most of
think
these bodies are almost certainly they've been reassembled. They have not they are not the original intact bodies that formed. Maybe Ceres, maybe Vesta, maybe Pallas, but I mean that's three out of millions.
okay.
Yeah, no,
Thanks.
that's a very good question. I haven't really thought about that. So I mean, I like these questions where it makes me think. So I'll have to do the research.
Let me chime in also that Mike, just so you know, Faith Vilas is kind of an expert on aqueous alteration and features and stuff like that too. And I think she's spent a lot of time thinking about that and what results in that zero point 0.7 micron feature.
Okay.
But I suspect it's different than what's happening on Mars, where you actually had liquids flowing on the surface, right? And I think on asteroids, we're talking about just getting to the point of being able to incorporate into the mineralogy to, getting enough heat to be able to incorporate into the mineralogy, not
Yeah, well,
flow
Mars is
across.
definitely a tangent, but I only raise that because there really are issues of how we had water on the surface. But yeah,
Sure.
that's definitely a rabbit hole. Let's not go down there.
Um, Tom, I wanted to ask about the space weathering thing. So you're gonna fake some space weathering on some um actual soils,
No, it's gonna
analytes.
artificially, you're gonna have to do it mathematically. The
Okay.
problem is if you look at the asteroids and you compare them directly to the meteorites, the asteroids, the S types,
Yeah.
are they're redder. And
Yeah.
so you can't classify if you classify the meteorites and then try to classify the asteroids, you're doomed to failure because the surface of the asteroid has been altered by the space weathering.
Yeah.
It doesn't work. So what you're going to have to do is do, and there are people do that mathematically, artificially space weather the meteorite spectra to look like the asteroids. So put
Yep.
in some nanophase iron, and people have done that and do it because you could classify the meteorite. We're positive we can classify the meteorite spectra, but I've had students who are in college and maybe in grad school now who've done it, but to classify the asteroids, you're going to have to spectrally alter it. You probably could do it in real life, but it's going to be a lot of work. So I think our first thing is to artificially redden the meteorite spectra and see can we can we physically classify the asteroid using the machine learning.
Are you going to do it for the primitive classes also? Because I think that the space weathering on those is less well understood than for the
Yeah, oh
asteroid.
yeah, yeah. What seems to be weird in the thing is the S types, it seems to redden the ordinary chondrites.
Right.
It tends to make bluer, the slope decreases. So in a perfect world, we want to do both. They seem to go the opposite way depending on what the composition is. If it's carbonaceous, it tends to like blue in the spectra, while the ordinary chondrites, it tends to redden.
Okay. I guess I wasn't clear that it was that
Yeah,
well understood for the C
it's
complex.
well understood in the way that we know something is happening, but it's good. It makes it an issue to write. I mean, that's the goal. That's the problem is we want to see can we get it to work for the meteorites first, and then
Okay.
we're going to have to put in what I don't want to use the word fake, but artificial asteroid spectra that classify that because there's a substantial difference in the reflectance of the meteorites and the asteroids that you can't directly compare them because the asteroid surface have been affected by the
Yep.
space environment, the higher energy particles, the impacts. So that's our thing. So our goal first is can we do the meteorites, and we believe we can, and then we're going to have to do stuff to do the asteroid because you're looking at the interior of the asteroids, but when you measure reflectance of an asteroid, you're looking at the top surface, the top microns.
Yep. Okay. Bea.
Are you also worried about particle size differences from, your meteorites and then compared to an asteroid surface?
Well, yes, we cognizant of because asteroids seem to be very, very fine grained. So that's why we're going through the Relab database. We're putting in like everything, different particle sizes, everything to try to make sure because we assume the asteroids, the surfaces are very, very fine grained. But when we train on the Relab data set, we have some very coarse grain. We also have very fine grain. We're trying to put everything in when we do the machine learning. But yeah, no, but I agree. The asteroids seem to be much finer, but we're not trying to we're trying to put everything so every possibility is open. In the machine learning, what we've done is I didn't want to go much into it because the thing with the machine, I've been working with a number of students, even high school students doing it, and it's not my expertise, the machine learning. I can see the results, but you applying it is, but the high school and the college student, this is like easy for them to do. But we're going to have a range of particle sizes. But I agree, the asteroids are much finer.
Okay. Nick.
I just want to say, first off, thanks for suggesting that there may be more than one parent body for the HEDs. That's something I've been arguing with people about for almost 2 decades now.
No,
Um,
it's obvious most I believe come from Vesta, but they don't all come from Vesta. It's obvious.
well, I was wondering if we could poke at your estimate for how many different parent bodies could be represented by the HED meteorites. You broke that out by looking at cap delta oxygen 17 and saying this is about how many different lines you can pull out from that. Yeah, that diagram.
Yeah,
Uh, sorry,
yeah,
yeah, that slide. There are several more that are missing from that, as you mentioned.
yeah,
So it's easy to draw a number of lines through that, but that's just cap delta oxygen. There's also similar evidence when you look at the chromium manganese isotopic systems that
yeah.
suggests there are several others. I was wondering if you looked at the intersecting space between that to see how many different groups the two of them combined would make.
No, I just use the oxide isotope. I would have no problem. My goal was, and I don't know, I like taking the average, guess the best estimate. When I say there's 10, it's 10, it's probably 10-ish.
Yeah,
So
it's order of 10.
yeah, it's an order of 10, but you can't get there's no way to get the exact number. I tried to put
Of
an
course.
it didn't go well in the review process. So
Hmm.
I just wanted to make sure I was just trying to figure out a way, is any way that I could get a number that seems relevant and stuff? Because there's lots of iron meteorites, but they're probably oversampling. I should look at that to look at the other numbers if the other isotopic systems. It's a very interesting, but a lot of these bodies formed, and only Vesta seemed to get, and I got lucky and survived to the present day. Everything else was just disrupted, but.
Yeah.
Vesta got lucky. That's my feeling. It just got lucky, and everything else was unlucky. It broke apart, and it all occurred probably right at the beginning of the solar system. So all the fragments and stuff, there's very few. They're all been just ground down to sizes we probably can't see.
Fair enough.
Yeah,
I mean, one of the things that got me interested in the question was some of the work in the early 90s by Amy Jurashevitz and
I
John
know.
Jones, looking at partial melting of a wide range of chondrites, but particularly the carbonaceous chondrites that you've mentioned a few times. Partially melt them under reducing conditions, you get something that looks like a eucrite.
Yeah,
That raises the question of, okay, was this ubiquitous? Because you grab a wide grab bag of things, you're going to end up with similar products if it was under similar conditions.
yeah. Yeah, definitely. Yeah. And this spectrum, the only reason I can do anything is this spectrum is so distinctive. This
Yeah.
HED is so distinctive. It comes out and it's easy to find. It's the one thing every survey that does any colors finds this immediately because it's so distinctive and it's very similar to mineralogy, maybe slight differences, but mineralogically, it only works if you have this low calcium pyroxene stuff. So yeah, no, I'd love to talk more about this. I found this fascinating. So it was just like a fun paper. We were invited to write for it was an Ed Scott Memorial issue, and then we said, okay, we'll come up with an interesting topic. So he said, okay, let's do it. And I like putting together evidence from different sources, not just the spectra, but look at the oxygen isotope, look at the iron meteorite, putting together to get the full picture. That's what I really love to do.
I hear you. Yeah, I'd love to talk more about this later.
Yeah, yeah.
Any other questions from anybody? Okay. Well, I don't see any hands, so I think we'll
I
leave
don't
it
know if
there.
that's good or bad, but
I think this has been a great discussion. Nice
okay.
seminar, lots of good work happening here, Tom. Thanks for
Oh, thank you very much
talking
for
to us.
letting me do this.
So we'll get this posted at least internally, so everybody
Yeah.
else can watch it. And yeah, sounds good. Thanks so much, Tom.
Thank you.
Okay, talk to you later.